All right. So tonight, what we're going to do is we're going to start with the sample midterm, actually sample midterm number one, because there are two of them. And in fact, if you look at Cengage real fast, you'll notice something interesting in there. B, the exams. Okay, so I finally got them all together. I was having issues getting it set up, and one of them wasn't written yet. So now it's all there very conveniently. Let's see, let's get that open. So where are they? Of course, they're not actually part of the regular MindTap assignments. So instead, if you look in your Cengage account, here we go. Remember always to use this as your menu, not this one. And you'll see, you go through and you see these are the ones, the regular ones that are due, 12 and 13, for example, are due this weekend. And then we just have 14 on Sunday the 2nd. But, oh, look, where did those come from? So those are the three exams. There's midterm, as you can see, one, two, and three. One, two, and three. One, two, and the final exam. Just in case it's not clear, by looking at them, it's broken up surprisingly evenly. We have, for the first midterm, chapters 9 through 10 only. Got to get this tablet set up. Oh, I know what went wrong. I forgot to plug it in. It is technically wireless, but I find that the wireless doesn't always work. So I always plug it in whenever I can. It's just safer that way. Okay, here we go. So it worked out nicely. Final is not comprehensive. It's just 13 and 14. Now, we haven't started 14 yet, but we will very soon. As soon as this sample midterm is done, we can start 14. That is our look at regression analysis, which is, in my opinion, maybe the most important topic in the course, because this is what you'll be doing if you end up using statistics in, let's say, research or in a job or some kind of teaching position. Research, everything's done with regression analysis, okay, especially in economics and finance. So this is kind of a big deal. So that we'll be going over maybe later on tonight. We'll get to that, but if not, certainly on Thursday. And so those are there. Now, if you notice, the due date is August the 3rd, one day after. So this is, I think that's a Monday. I only did that because I want to make sure you have the maximum amount of time to work on these. And the grades are due like maybe the 6th or something like that. So luckily though, with MindTap, I mean, a lot of that is already being done directly. It's calculating your averages and all, but still, I wanted to make sure that I do this carefully and properly, get your grades ready in a timely manner. And I see a few of you have already started these. That's pretty cool. You can do them whenever you want, especially if you think you might be going away on vacation later on in the summer or later on during the course. If you have other commitments that might come up, you want to get these out of the way sooner rather than later. You can work on them in bits and pieces. You can start it and then save it, etc. But just be aware that it will only allow you one attempt at each question instead of the usual three. Although I believe it's still giving you helpful hints, because it's a different category. When I set things up in here, it asks like, is this an assignment or is it a test? And by telling it a test, that changes the way it's set up. So it's more, I wouldn't say unforgiving, but it's not as easy to, get more attempts as, let's say, in one of these. So anyway, let's get to this thing. I just opened it up a few minutes ago. If you look in Blackboard, You'll see that there are folders for sample midterm number 1, number 2, sample final, sorry, the actual final is sample final, sorry, the sample final is right here. Okay. So they're all here if you were wondering where they are. And of course, chapter 14 is way down here. It does have two parts to it, and there is some Excel associated with it. So it'll take a while to get through it, but in fact, I'm going to open this up right now just to give you a quick preview of what's coming. Here we go. All right, so this is 14A. So they're going to introduce the simple linear regression model as opposed to the multiple regression model, which comes in chapter 15, which is not part of this course. But if you need it for, let's say you're doing a research project or something else, you know that it's in there, okay? The method we're using is called least squares. The coefficient of determination is one of the measures we use to determine the quality of results. And like so many other applications we've looked at, there are assumptions going on that we need to be aware of because, let's face it, we have to make sure that our results make sense. And so if our assumptions are not being met, that greatly reduces the chances of our results being meaningful. And then testing for significance. So that's a lot. That's a lot. It's a very big topic, let's say. But then we also have this spreadsheet, Armand's Pizza, that'll help us learn how this regression analysis is implemented. And of course, we'll be able to use some Excel. And so, it's one of those topics that looks really scary when you first see it, but it really isn't once you get used to it. And in this chapter, we'll see that we'll use the T distribution as well as the F. Okay, so that's why they introduced it to us so early on, because we do need both of these. We don't need the normal, believe it or not. That's kind of unusual, but here we don't use it. But we do need both T and F. Oh, here it is. Now B, what B is doing is first we're learning about how Excel handles this, but we're also using the output from our regression analysis to make some basically quality checks about our results. And in other words, the focus here is on helping us understand if our assumptions are being met or not. There's a lot of assumptions with regression analysis. And what can happen here is that if they're violated, sometimes there are ways we can correct for that, and sometimes there are not. So we need to be aware of if the problem can be corrected, and if not, what is it likely to do to our results? All right, so that's 14. So right now, let's get back to this sample midterm. Now, by the way, these sample midterms were written for the in-person class. In other words, I used this last fall for a class that was meeting not online, but in person. So that's a different scenario because then the exams are being done in the classroom as opposed to here where you're at home and doing it online. So these types of questions, they could theoretically appear on your exams. There are some multiple choices in there, and some of them are just straight ahead definitions, but I don't want to completely gloss over this, but it's not quite as important as it would be if you're taking this exam in the classroom. So we'll run through these anyway to help refresh our memory as to what all of this is about. But our focus is going to be on these problems, okay? And that's as it should be. So for example, let's remind ourselves, what is a type 1 error? Okay, now when you see that, you're going to think to yourself, oh, do I really remember this? Well, luckily you can go back and visit the slides and say, oh, that's right, I remember this now. Same thing, with the handwritten notes that I put together. So exactly what is a type 1 error? Actually, I'll tell you what, let me copy these so I don't have to keep writing them. Writing them out by hand is very slow compared to typing. All right, so what is a type 1 error? What did it do? Oh, I really can't stand it when it does that automatic indentation. If I can get rid of it. Sometimes if you fight with it long enough, it comes back and says, do you really want me to stop doing that? Um, Answer is yes. All right, I'll tell you what, hold on. Yeah, as far as I'm concerned, I'll do the thinking. I want to tell the software, you know what? Thanks for trying to help, but I'll do this myself. Don't worry. So I'm hoping that that will fix this little problem. There you go. All right. Anyway, type 1 error. This refers to the probability, or actually, the probability that alpha is the type 1 error probability. What they really want to know is, so with a type 1 error, this means reject the null hypothesis when it is false. And so I'll put in parentheses, even though they didn't ask about this, a type 2 error means to fail to reject the null hypothesis when it is false. Oh, I'm sorry. I just realized I goofed this up royally. This should have said true. Reject the null when it is true. If we reject it when it's false, it's not an error. So reject the null when it is true is type 1 error. Type 2 error means fail to reject the null when it is false. All right, now we're good. And also don't forget the alpha that we keep seeing throughout these chapters is the probability of a type 1 error. Okay. So when you see an alpha by itself, you know that it means the probability of a type 1 error. All right. The null hypothesis, this is a statement that is assumed to be true unless there is strong contradictory evidence. And then you would reject it, of course. Now, when conducting a right-tailed test, about a single population mean, the null, all right, so we got to watch it here. The alternative is this. In general terms, if we don't know what we're comparing it with, the null would therefore be this. Okay, so it's a right tail test about a single mean, and this is how we know that. And then the null covers everything else, and that's why it looks like this. Okay. Now, when testing hypotheses about a single population mean, meaning chapter 9, and sigma is unknown, the test statistic is based on the t-distribution, and this is what it looks like. All right. Hypothesis tests about the population proportion are always based on which probability distribution. That would be standard normal, or Z. Okay. In other words, what they're saying here is that unlike with the population mean, where sometimes we use the t distribution, sometimes the standard normal, here it's always standard normal. You never use the t when you're testing anything about population proportions. Okay. All right. For two-tailed tests of a single population mean, when the population standard deviation is unknown, critical values will therefore be, because it's a two-tailed test, okay, so remember, this is the degrees of freedom, and these are the two tails that each contain half of alpha. All right, 7, if the p-value is less than or equal to the level of significance, meaning this, of course, that means we reject the null hypothesis and accept the alternative. So the answer to the question is yes. I mean, if this showed up in MindTap, yes would have to do the job. Now, this is kind of an interesting conceptual question. It's getting to the idea that there is always a trade-off between the probability of a type 1 error and a type 2 error. In other words, to have less of one, you have to accept more of the other, and vice versa. Okay. So that being the case, remember the level of significance is the probability of a type 1 error. Therefore, if that goes up, the probability of a type 2 error has to go down. So the probability of a type 2 error decreases. So if one goes up, the other has to go down, and vice versa. 9, when using the p-value approach to hypothesis testing, what must be true to reject the null hypothesis? That would be p less than or equal to alpha. Okay. Now, when we're testing a hypothesis about two population means, when they're not independent, That would be our matched pairs case. It's a very convoluted way of saying matched pairs. And then when we have matched pairs, we always use the t distribution. Okay. So, these are some pretty typical fill-ins, but, they're going to be less important here because we're doing this online. So which is the first of our word problems? Now, keep in mind, a lot of times with these types of problems, the challenge is getting the wording right. It so often happens that the wording is not clear as it could be. At least, well, in textbooks, that is. I find that to be the case. I try very hard to make sure that doesn't happen. So a juice manufacturer wants to ensure that its orange juice contains at least 50 milligrams of vitamin C per 32-ounce carton. If that's not the case, the manufacturer will use a more expensive type of orange in the production process. So that means we're assuming that this is true unless we have evidence to suggest otherwise. So the alternative is that the orange juice does not have enough vitamin C in it. The null is that it does. So in other words, it's a left-tailed test. Okay. So again, you've got to read these questions very, very carefully because, sometimes, like I said, the way they're worded, it's not super obvious what you're trying to do. So they're giving us an alpha of 0.01. And also there's some data here. I'll put it over on this side. We took a sample of 20 cartons. The sample mean is 48 milligrams. And the sample standard deviation is 2.4. So that is how we determine our test statistic and our critical values, knowing S instead of sigma. Okay, so we plug these in. And let's see what we get. Oh, all right, I made a dumb typo and now I was trying to correct it and it just wouldn't work. Oh, okay. I know what happened. It's negative 3.73, which is quite small. For the t distribution, that is a very, very negative number. The critical value, there's only one because it's a left-tailed test. And remember, in this part of the book, we're using n minus 1 for our degrees of freedom. So the alpha was given to us as 0.01, and the sample size was 20. So we have 19 degrees of freedom. Now we have to go look it up in the calculator. All right, so we have to do second vars, number 4, INVT. Oops, wrong one. Then it asks for area, which is the left tail area, of course. And these two, oh, I've got the wrong one. Hold on. I hit the wrong. And so the degrees of freedom is 9. Yeah, it's 19. Enter. Approximately negative 2.54, let's say. All right. So that makes it easier to make a decision. This is our rejection region. And of course, our test statistic was quite a bit larger than that, negative 373. And because we're in the rejection region, we reject the null, which if you remember is mu is greater than or equal to 50. And we accept the alternative that it's not. Now, you know what that means. The company has enough proof that there's not enough vitamin C in these cartons, and that means they will have to change the oranges that they're using. That's going to lower their profits. They won't be happy about this. All right. And then what about the p-value approach? So our test statistic is negative 373. Anything more extreme than that constitutes our p-value. So we can go to the calculator and look under second vars, number 6 TCDF. And when you get there, it'll ask lower. Negative infinity, of course, we don't have that here. So instead, we use negative E99. Upper is the negative 373. Degrees of freedom, as we just saw, is 19 because the sample size is 20. All right, let's see what it is. Oh my God, it's so small that it's in scientific notation. I remember what that means. This is shorthand for. That's a tiny number. That means there are three leading zeros. Now, clearly, P is well below alpha, and so therefore we reject the null and accept the alternative that the mean is too low. Not 250, 50. So that's how we know that we need to do something different with the orange juice. Okay, that was number one. Very straightforward, good practice. What about number two? A small museum wishes to determine, I don't know why it keeps changing the font. If the average age of its Greek sculptures is greater than 2,000 years. That, of course, belongs in the alternative hypothesis that the mean is less than or equal to 2,000. Test this at the 5% level. And on the side, we'll put some of our data. We have 24 sculptures. The mean is 2010. And the sample standard deviation is 220. So we know that we're going to use the t distribution, not the standard normal. All right, so here's the test statistic. Let's see what it gives us. This is 220. We divide it by the square root of 24. All right, let's see what this is. Ooh, that's a very, very small number for the t distribution. So it's not likely that we'll be rejecting this null hypothesis, but let's check it out. So it is a right tail test, so the critical value is t. And again, we have a sample size of 24. Sigma is 0.05. Alpha is not sigma, alpha. To go to second vars, go for number 4 INVT. And then of course, it wants an area and degrees of freedom. Area would be 0.95. Degrees of freedom is 23. All right, let's try it. 0.714, let's say. Anything above that, of course, means we reject the null. But our test statistic was so tiny. It was only 0.222. And that's well within the, well, it's not, I should say it's not in the rejection region. And so therefore we do not reject the null. Um, that the mean was less than or equal to 2000. Um, and that's it. We do not reject it. So the answer to their question, they want to know if the average age is greater than 2000 years. And the answer is no, or at least we don't have any evidence of it. Okay. So in other words, the actual age is less than or equal to 2000. And of course, we can do this as a p-value as well. So remember, the test statistic is, I mean, it's 0.222, and it is a right tail test. So for that, we're going to calculate um, and so we know how to do that. Yes. And what we have to do is go to second vars. And then we want number 6. Which is TCDF. We'll ask for lower, upper degrees of freedom. So remember, the sample size for the statues is 24. So there's 23 degrees of freedom. Okay, anything in that region means we would reject the null. All right, let's see what that number is. Mm-hmm. 0.4131. So remember, this is the p-test, so you're comparing the test statistic with the uh, with the alpha. So in other words, this area is more extreme than the test statistic. And so if we end up with a p-value that's less than or equal to alpha, then we have to reject the null. But here, that's not going to happen, is it? No, because this is our p-value. I think the alpha for this one is 0.05, but let's just confirm that. Yes, 0.05. So clearly the p-value is well above alpha, and that means do not reject. C is okay. So, um, of course, these two approaches have to confirm each other. Do not reject the null. Do not reject the null. All right. What's next? Well, here we have one with two populations being compared to each other. There we go. Okay. So an insurance company wishes to determine if the mean age of its male and female employees, policyholders is equal. Let's see. Now this is normally well, we normally do not assume that variances are equal unless there's some reason that we should assume that. So the test statistic for this one, I'll remind you, is written in a somewhat peculiar way. Okay, and remember, this is the hypothesized difference, which is usually zero. So they want to know if the mean age of its men and women customers or policyholders is equal, therefore the difference would be zero. So we can just let that drop out. And we're being told that among the men, well, first there's a sample of 50 of each. Among the men, the sample mean age is 42. Oh, sorry. The next statement is that the sample standard deviation for the men is 2.4. Now, what about the women? The X2 bar, there it is. It's 39. And the sample standard deviation is 3.1. There we go. And we have to test this hypothesis at the 5% level of significance. So, first let's write down the hypotheses. So, wait a minute. Oh, here it is. So you notice how the way the question was worded, they want to know if the mean age is the same or equal, which means that the alternative is that they're not equal. It's a two-tailed test. All right, the alpha, as we can see here, is 0.05. The test statistic. Now this is the one, mind you, in a second. Yeah, it looks a little strange, but S1 squared, S2 squared, over N1, N2. This is 0 in this case. All right, so we start plugging in some numbers. What do we have? 42 minus 39. And then we were given some variances and standard deviations. The min is 2.4. And I believe there are 50, yeah, 50 of them. And then we have, for the women, the standard deviation is 3.1. Again, over 50. So if you pop that all into your calculator, double checking my results here. All right, I'll try. I'm going to write these down in stages. Okay, let's see what that turns out to be. 5.41. Well, that sounds like a very large number, but it is correct. Now, since this is one is a two-tailed test, test statistic is actually quite, oh, I see. You know, what the holdup with this one is the critical values require the really messy formula for degrees of freedom. I'll just write that as DF. And it turns out if you go through that formula, I'll just stipulate this for you. You'll get 92 approximately for the degrees of freedom. Yes, alpha is 0.05, so half of that is 0.25. Okay, and that one's negative. Okay. All right, so we can certainly look up either one of them because they have the same, it's the same number with two different signs. All right, INVT, area and degrees of freedom. So as of right now, that's 92, area is 0.025. And let's see what we get. Negative 0.986. Okay. So here we have, and what do we compare this with? Well, the test statistic is 5.41. Okay. Got a little meter. Okay. So that's our test statistic. It's clearly well within the rejection region. Okay. And I also want to try the p-value approach. So let's draw that diagram again. 5.41 is our test statistic. So we need to look at the probability. Okay. So we go to second vars. And now what we're looking for is INVT number 4. Oh, wait, sorry. What am I saying? No, this is the probability. The INVT is to find the location. This is a probability. It's not 4, it's 6. Okay, 6 TCDF. So lower is the 541. Upper, I think that's pretty far up. I'd have to go with infinity on that one. All right, here we go. N degrees of freedom. Remember, in this case, I've decided to give it to you directly. It's 92. Oh, look at this. Et cetera. E to the minus 7. Oh my God, that's a tiny number. Well, it's, where is it? Oh, there it is. Mu1 minus mu2 equals 0. Except the alternative, which is, I don't know, let's see. Okay, so let's see. Let me get this out of the way. Oh, you know what? I just realized something. Um, because this is the p-value, we were supposed to double this. That doesn't change anything. I just realized uh, scrolling through here, we forgot about this detail. Because there's a two-tailed test, you have to multiply that by 2 to get the true p-value. So doubling that would bring it to 0.49, 652 e minus 7, which again is a preposterously small number, well below alpha. So therefore, we're going to reject the null. All right, very good. So, in other words, going way, way back, the differences between them are significant. That's really the bottom line. And it also, now there could be something else going on. Like somebody might ask, why are the two being charged different um, premiums? And, because we can see proof that their ages are not the same. So therefore they can justify it. what's next? Aha. Now, as soon as you see this little table, you know we're talking about matched pairs. Let's be consistent here. Let's make this into Times New Roman. Now, here we're looking at some kind of an exam. So the premise of it is that students take the test with the original technique, whatever it was. Then they learn the new technique and they try the exam again. Now, of course, we want the means to go up. But the hypothesis is written as we want to find out if the scores went up. That would imply that mu1 minus mu2 is actually negative. Because it's the same thing as saying that mu2 is greater than mu1. And that's what you would get if the new technique is better. So the null would be that it's, they're not, it's not an improvement. So the alternative is that the new scores, it's actually not the scores, it's the technique that we're using to study for them. Let me fix that. Better. So now here's something else we should probably do. First things first, make a new column for the differences, because that's ultimately what we're after. So it's the first minus the second, minus 3, positive 8, minus 8, minus 4, minus 1. Those are the differences, and those are what we're going to use to come up with our test statistic. Right. Now remember, this is the one that's written a little differently. Oh, I see what I did up here. No, with matched pairs, these are not wrong, but you normally write it like this. Okay, the mu with the little d is there to remind you that this is the mean of the differences, not the actual values. So the test statistic. Now, you may remember that we decided that our best bet here is to use um, the calculator to help us out. So let's do that. Okay, so yeah, we could do this ourselves, but it would be kind of a nuisance. So what you need to do is enter those differences into the list. So you go to stat, enter, and clear out one of the lists or use a different one. It doesn't really matter. So the numbers we want are right here, -3, 8, -8, -4, -1, and 2. So now, once that's done, you go to Stat, but this time you choose Calc in the middle. And the one you want is in the very top, one var stats. Just hit enter again. Now it's going to ask you, where did you put your data? So, I put it in list one. You could do whichever one you want, but make sure that you tell the calculator where your data are. All right, here we go. Oh, God, what happened? There we go. So what you need is the two things. This is -1, and this one is 5.5136. So we're going to do this. Plug in the numbers you just got. And also don't forget n is 6. There's 6 matched pairs. So the D bar is -1. Then we have 5.5136. All right, and here it is. -0.444. Okay. Now, of course, we can use the test statistic critical value approach right now. So the critical value is this one is n-1, that's right, because we're only looking at the differences. Alpha is 0.05. We can go to second vars, number 4 einbeat. And it will ask us for area. Now, this one is in the left tail, so area is actually that alpha there. Okay. And the degrees of freedom is 5, n-1. And that leaves us with negative 2.0. Oh, I just realized, you know what? No, the alpha is not 0.05, it's 0.10. Let's go back and read the question again. I no, you know what it is? Right from the beginning, I copied it wrong. All right. Let's see what difference that makes. One with 5 degrees of freedom. Yeah, that's more like it. Negative 1.476. The statistic is only negative 0.444. So, of course, that means we do not reject the null, which is, forgot already. Here it is. That mu d is greater than or equal to 0. By not being able to reject this null, that shows us that there is no valid proof that the new score is better, the new technique is better than the old one. Okay. Now, of course, it's possible too that, other issues are involved, but that's what this means. So here the test statistic was negative 0.444. It's a left-tailed test. Okay. So keep in mind that we have 5 degrees of freedom. So we go to second vars. Area is the left tail, which is, oh, wait a minute. Do I have the wrong one? Yes, I do. Sorry, I'm looking for the probability, not IMVT, TCDF. Okay, so oh God, I hit the wrong thing again. I hit the wrong button twice in a row. Oh, no, no. Sometimes when it gets confused when you hit the wrong button, you have to basically just turn it on and off because otherwise it'll keep leaving old information in the memory. That's what was happening. It kept going back to that same function. Ah, now we're talking. Lower and upper. Upper is the negative 0.444. Degrees of freedom is still 5. And we get 0.33. 7, 8. Alpha, though, 0.10. And that, of course, means do not reject the null. And the null was that mu d is greater than or equal to 0. So anyway, you look at it, we do not reject the null. And that means that there's no evidence that the new technique works better than the old technique. All right. Let me just sneak that in here. Is there another one? Oh, there are others. Okay. That's fine. We need the practice. We've been neglecting proportions. So in order to improve the efficiency of its inventory systems, Starbucks is interested in determining if the proportion of decaf that it sells is 20%. Okay, now because of the way they said that, is it 20 or not? That means this is a two-tailed test. Okay. Now, alpha is 5%. Now, since this is a proportion problem, we don't have to worry about using t. It's not going to happen. And so the data we were given is that we have 200 customers, 147 of them. See, oh, this is written in a little slightly tricky way. This is what we need to know right here. Be careful. 53 say they drink decaf. That's what we're analyzing. What proportion of them like decaf? So don't be tricked. And so here we can conclude that sample proportion is 53 over 200, which is about 0.265. All right, so what test statistic do we use in this case? Now, you might recognize this, it's been a while. So you're comparing the sample proportion with the hypothesized proportion. Down here, we have this term standard error of p bar, which itself is defined as. So it's p0. So here we have the hypothesized value p0 is 0.20. So therefore, let's start with this term. This, as you recall, is the standard error of p bar. Sample size was 200. All right, let's see what that is. About 0.02828. So the numerator is p bar minus p0. And we determine the p bar is 0.265. It's almost exactly 2.3. All right, so there's our test statistic, the critical value test. And the alpha, once again, was 0.05. So we can go to second vars to find these. Number 3 is INV norm. And it's going to ask for area, meaning left tail area, mu and sigma. And that gives us negative 1.96. Okay. So those are the critical values. And the test statistic was 2.3. So clearly the null is rejected. And we accept the alternative that it is not 20. So now they're saying that the proportion who like decaf is different from 20%. Oh, of course we can find the p-value. So it was positive 2.3, but this is a two-tailed test, so we need the negative as well. And so, hold on one second. I need to give myself more room. Here we go. So we're going to do 2 times probability z is greater than or equal to 2.30 because, of course, each tail is the same area. All right, so it's going to have lower upper. All right. Wait, 0.01. But remember, we have to double this. So we end up with 0.0214. But remember, the alpha is 0.05, I remember. Yeah, there it is. Okay. All right, reject the null that they're equal to 0.20. Okay. So in other words, once again, we have evidence that the proportion is not 0.20. And then they will make the decision what to do about that. Like how does it affect the way we produce the coffee? All they wanted was yes or no. Is it 0.20 or not? And we've shown that it is not. All right. So in other words, we're the statisticians. They can make the decisions. We just give them the numbers. Now, here comes, oh, ice cream. Breyers is conducting a study to determine if the proportion of the customers who prefer vanilla and chocolate, um, yeah, the proportion. They want to know if they're different between American and Canadian customers. If they are different, they will change the methods being used to advertise Breyers. So let's gather some data. 100 Americans, 100 Canadians. Americans who prefer chocolate is 184 for Canadians. It's 77. So it's 92 in America. And it's slightly less than that. Well, it's somewhat less. 77% in Canada. All right. So, and we have the 5% level of significance. So the null, yeah, it's a straight ahead two-tailed test. Now, this test statistic, oh my God. It's a big one. P bar here is defined as is this. Okay. So if you plug these in, let's see what this is equal to. Point 87. That's the average between the two countries. So now we can pop everything into here. Ooh, yeah, that's a tough one. All right, let's try this. So this is one of those cases where you might be better off doing it in two stages. For the denominator, Huh. Let's see what that turns out to be. Wait, that's about 3.64. Okay. Now, this one is a two-tailed test and an alpha of 0.05. And we saw one of the earlier problems. We don't have to look this up again because it's just 196. Okay. We had that earlier tonight. So we're going to lean on our memories. All right, but the 364, that's way out here. So therefore, we clearly reject the null that the proportions are equal in favor of the alternative that they are not equal. Now, you can kind of tell. I mean, it was 92% for the Americans and 77% for the Canadians. So, um, yeah, that didn't seem very close to it. No. So all we can do here is say that the proportions are not equal. What am I doing? The proportions are not equal. And again, we can do a p-value. And since this is a two-tailed test, we need both the positive and negative tails. And so we're going to need whichever tail we can calculate and then double it. Okay. And that turns out to be 90 numbers again. The scientific notation is involved. 1.364 e minus 4. When we multiply that by 2 to get the p-value, 2 point, it's still scientific notation. Now, clearly, that's way below alpha. So we reject the null that the proportions are equal and accept the alternative that they're not. So the bottom line is Canadians and Americans have different tastes when it comes to ice cream, according to this problem. Okay. I don't know if it's true in the real world, but with this data, that's what we conclude from all this. Now, the only piece left is there's a confidence interval in here that we'd like to look at. We've been kind of neglecting the confidence intervals. The book seems to love them. Okay. So yeah, they're referring back to the same data. They'd like us to calculate a confidence interval. Now, in order to do that, we have to remind ourselves what this formula looks like. And so we'll just go back and revisit now. I'm going to use a little clever trick here. I'm going to split the screen so I can scroll back here and quickly review the data. There we go. So the two of them were 0.92 minus 0.77. And then we're probably going to run out of room. I'll write it like this. E1 bar. Oh, we already have it. And one minus that is clearly 0.08. We had 200 Americans in our sample, the Canadians. All right, that should do it. Oh, of course, this term is our point estimate. And everything on the right-hand side is the margin of error. All right, let's see what we can do with that. Actually, you know what I'm going to do? I'll I'll just do it all at once. All right, I'll just do the calculations and see what the margin of error is. So if you do all of that, I got 0906. Yep, that's it. All right. So when you subtract, Lower limit is 0.0594. The upper is 0.2406. Well, that was an ordeal, wasn't it? But now we're 100% ready for that old midterm because it's got to be very similar to this. Okay. Wow. So that leaves us just a little bit of time to reintroduce ourselves to chapter 8. So we'll work on 8. What am I saying? Chapter 14, sorry. Chapter 14, regression analysis. This is going to take a while, as you can imagine. And when it's done, we can switch back to sample midterm number 2, as well as the sample final. Now, luckily, the calculators can help us out with this one. If we put our data into lists, we do have routines in the calculator that will help us with this. We also, of course, have Excel. Excel has a lot of powerful features here. So we'll do both of these as we go along. And I think we started to discuss this the other day. This is the population regression line. And this is based on the entire underlying population. Now, what are these terms? Well, this is this intercept, and this is the slope. Okay. Now, this is the error term, which is something you don't normally see because all the points in our data set are not perfectly uh, related to each other. In other words, if you plot all your data, a scatter plot, each point representing one observation, you'll notice that these points are kind of somewhat randomly scattered around. There is a definite upward trend here, but the points for the most part are not on that line. So the error term is designed to capture the distances between actual values of y in the data set and the predicted values as represented by that trend line. So the line is a prediction. The points of the dots are actual numbers. So the epsilon, each point gets an epsilon. The epsilon is positive for points above the line. It's negative for points below the line. And of course, it would just be 0 for the points that are exactly on the line. Okay. Um, So when you draw a regression line, let's say all your values are positive, so we're in the first quadrant. This line is where we would be if all the epsilons were zeros, meaning that this is the actual linear relationship underlying the data. So you can think of this as the population regression line. So, you might run across regression lines with a positive slope. And if that happens, that means that X and Y are positively correlated. If the slope is negative, negatively correlated. And of course, zero means that X and Y are uncorrelated or independent. Now, of course, we can't actually observe the entire population. So while this is our population regression line, I want to put them together so you can see how they are different. Here, you get a few different terms. This is the sample regression line. It's very no nonsense to say the least, okay? And this symbol is called the caret. It's often used in econometrics, advanced statistics, and to represent an estimate or an estimator. So also notice that we're switching back to the Roman alphabet here, because we're now looking at a sample. Okay. Now, I mentioned this, I think, before. What we're going to do in this chapter is use this technique. There's many different ways we can estimate a regression line. We're going to use the so-called least squares method, sometimes known as ordinary least squares. We abbreviate it OLS. So the line is obtained, that regression line, by placing it in such a way that the differences between the actual, that that one should be called predicted. And the vertical distance between them is that epsilon that we mentioned earlier. Right here, they want to introduce us to this idea that we're trying to get the points as close as possible to that line. So notation-wise, this is what we're looking at. Here we go. That's the value that we estimated with the regression line. The actual y up here, but this is known as simply y1. So the little pointy hat thing here means this is an estimated. And this is the actual y. So then they're going to tell us that. Let me just double check. I want to make sure I remember his notation. I think he's using lowercase e. Let's just say that it's e. Because so for each x, there's an actual y, there's an estimated y, and an error term. The properties of the error terms can actually give us a lot of insights into what we're doing, especially whether our assumptions are being met. Okay, let's get back up here. But anyway, the min means minimum. In other words, we're trying to find the line itself is constructed by keeping the distance between the y's and the estimated y's down to a minimum. So they'll write it like this. Minimize the sum of these vertical distances. Okay, and that will give you your line. Oh, I almost forgot the square. So using this approach is what we mean by the ordinary least squares approach. In other words, ordinary least squares refers to right here. How do you find the points on your regression line with that besides the real data you have? This is how it's done. This is the OLS method, ordinary least squares. Okay, now if you recall, here it is, the sample regression line looks like this. Y with a little hat, as it's called. Okay. Yeah. Um, Yeah, I'm just making sure because again, every book uses slightly different notation. Okay. So what they're going to do here is show you. Now, this is something we don't want to spend a whole lot of time with this, but you can do this by hand. The formula for the B1, meaning the slope of your sample regression line, is this. A lot of work. Zero is here. Okay. So clearly you have to do B1 first. And then you've got your sample regression line. All right. Now, I think we're going to, oh my God, look at all that data that we need. Here's Armand's Pizzerias. Data was collected from 10 Armand's Pizza Parlor shops with near campuses for the ITHA observation or the restaurant in the sample. XI is the size of the student population. YI is the sales. Here's the data. And they're plugging it in so you can see why, because they need this B term. And you can see it's a very complicated thing to calculate. And then we need the bars, the Y and X bar, which are the means. And that gives us our slope and our intercept. So at the moment, without any better information, this is our best predictor of the value of Y hat for every given value of X. So we are going to do this ourselves. We're going to go back and try this with a chart with the calculators, and then we're going to do it with our friend Excel here, not to mention a graph that we're going to put together. Now this is the coefficient of determination. What they're building up to here is one thing that we have to be constantly aware of with regression analysis is that we have to always check to see if the results make sense. Because you could have two random sets of data that are unrelated to each other and still create a regression line. So you have to have a way of saying, well, this one makes sense and this one doesn't. So they're going to start introducing in small stages these different measures to help us understand what's going on with our regression data. And so here they're doing this mess here to build up to this idea of R squared, the coefficient of determination. It's the kind of number that you want it to be as close to one as possible. But it doesn't always work out that way. So, but it's good to know what it is. All right. Let's see. Assumptions about the error term. Then at some point, we're going to actually do some calculations, some actual tests. Ah, like it. There it is. And again, you'll kind of get used to it pretty quickly. Okay, so this is 18. So, all right. Now, so today's Wednesday. So I guess what we should do is tomorrow, just nothing but regression. We're going to get through all of these notes if we can. And then we're going to work on maybe one of the spreadsheets. Now, don't forget too, I'm going to make a new recording over the weekend to make up for yesterday's flooding. And which I didn't see a whole lot in the city, but man, it was bad where I live. Cars were like floating almost. But anyway, and then so our goal is to wrap up 14 and then do the second sample midterm as well as the sample final. And then that will be the end of the coursework. And then what remains is for you to finish up all the assignments, and then we'll be done. So we're getting close to the end. We're not there yet. We're getting close. It's like the light is at the end of the tunnel. So again, we're kind of in the early stages of 14. We'll get deeply into that tomorrow, and then we can wrap up the reviewing, and then we'll be all set. And then you will no longer, when you go back in the fall, you'll say, wait a minute, I don't have to take stats two. I did it during the summer. My schedule is light and breezy, and this is why. Okay, so it's not easy doing this stuff during the summer. It's also, it takes a little getting used to do this online too. It's not for everyone. It's not the same experience at all. But you know what? If it's better than nothing, if it's either that or nothing, you definitely want to try it online. So, all right, anyway, so we'll stop it right here, and I'll see you all tomorrow night. All right, see you then.
Thank you.
Thank you.
Thank you.
Bye. Bye. Good night.